All right, so we have spent a couple days talking about the concept of electron configuration. And with electron configuration, we've identified the different sublevels that we can see pictured on the periodic table. Remember S, P, D, and F. And we've talked about how we can identify those. We've talked about how each period, or row on the periodic table, represents an energy level. What we're going to talk about now is the concept of valence electrons, and using a structure called a Lewis dot structure to identify these valence electrons. Valence electrons are extremely important because these electrons are the electrons found in the outermost energy level. Okay, so the outer shell, these electrons are called valence. Okay, and the reason they're so important is because these electrons are the ones that are going to come in contact with other atoms first. So one element has valence electrons, another element has their valence electrons. Those electrons are going to interact with each other before other electrons do. So those are going to be the ones that we will consider most likely in the bonding process. And we'll talk more about bonding next unit, and how we use these valence electrons to identify what types of bonds we can form. And another thing that valence electrons do, they are helpful in helping us predict what is called oxidation numbers. And again, oxidation numbers, like bonding, we'll talk about that next unit. So let's go back to the concept of valence electrons. Just like any periodic trend, atomic radius, ionization energy, electronegativity, we can also identify the valence electrons by looking at the periodic table. But they're specifically found in the S and P subshells. So outer energy level S and P electrons. Okay, and we can identify these based on the groups. So let's go ahead and label these. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Okay, now it would make sense for us to go right here to scandium and just continue with 3. But these guys are the transition metals. And because they're the transition metals, they have different oxidation numbers depending on what type of compounds they make. So we actually skip the transition metals when we are talking about Lewis dot structures. So we'll pick up the 3rd valence electron right here with boron, or group 13. Remember, valence electrons are only in the outer energy level S and P. So 3rd one picks up in the P subshell, 4, 5, 6, 7, and finally 8. Notice, here is my last group and my highest number of valence electrons, 8. So the maximum number of valence electrons that I can have, or the maximum number of outer energy level electrons I can have, is 8. Notice group 8 has a full valence shell. Group 18, also called the noble gases. We've talked about these guys before. Remember, we talked about the noble gases do not like to react with other elements. Well, now you kind of have an understanding of why that happens. Because noble gases, remember, are inert, are essentially unreactive. They have a full valence shell. They have 8 valence electrons. They don't want to gain any more. They don't want to lose any. They're happy just the way that they are. So all elements are actually trying to attain that full valence shell when they bond, and we'll talk more about that in a later unit. Let's talk about the steps in drawing these Lewis structures. So again, group 1, we know, has 1 valence electron. Group 2, 2 valence electrons. Pick up the 3rd one in group 13, and we go all the way down to a maximum of 8 valence electrons. The first step in drawing these Lewis structures is to, 1, identify where the element is on the periodic table. Identify the group where the element resides. So identify the group where the element resides. So basically, where is this element on the periodic table? Once we've identified the group, we can count the number, count or simply identify the number of valence electrons. And again, we get these valence electrons, or the number of valence electrons, by simply looking at the periodic table, knowing what group that element resides in. The last thing that we'll do is draw the symbol. That's our central part of this structure. Draw the symbol. Then place dots around the symbol to identify the total valence electrons. Place the dots around the symbol to identify those valence electrons. So let's look at what that would look like. Okay. First off, our first example here is potassium. Notice potassium on the periodic table, it's in group 1. Okay. All of group 1 elements, lithium, sodium, potassium, rubidium, cesium, francium, all of those have something very similar in common. Okay. And that is, being group 1, they're the alkali metals, they have only one electron in their outer energy level. So, understanding it's in group 1, only has one valence electron, we can simply draw that electron or place a dot next to potassium. That is the Lewis structure for potassium. Pretty simple, one dot, one valence electron. Notice we have not shown all of potassium's electrons. Remember, it has 19. All we've shown is the valence electron, or the outer energy level. Okay, let's do aluminum. Aluminum, group 13. Here it is, way over there. Group 13, notice up at the top, this Roman numeral 3. Group 13, our group 3A, Roman numeral 3A elements have 3 electrons in their outer energy level. And let's identify those, placing a dot, 3 dots to show each of those valence electrons. Now, I'm going to stop right here and just tell you that I prefer following a pattern going right, left, top, bottom. But it does not matter where you put those electrons as long as you understand you can only have a maximum of 2 on each side, and the maximum number of electrons that you can represent, or the maximum number of valence electrons you can represent, is 8. So it doesn't matter where you put them. If you wanted to put the 3 for aluminum in a different pattern, go right ahead. Maybe you like left, top, right, or any way that you see fit, just as long as you understand they will be by themselves until you have enough that they have to pair up. So let's look at phosphorus and what that would look like. Phosphorus, group 15, has 5 valence electrons. We're going to represent all 5 of those valence electrons. We'll start right, left, top, bottom, and then the 5th one will come in and pair up with one that we've already placed there. So notice 2 on one side and then 3 individual electrons all around. Okay, we'll skip over to krypton, our noble gas. Remember krypton, way over here, group 18, we've got our noble gases having a full valence shell. We'll represent all 8 of those valence electrons here, and I'll show you what that looks like. Krypton, 1, 2, 3, 4. Okay, each side has 1 valence electron, but I still have 4 more to place, so I'm going to go in now and pair those up. So, there's krypton with its full valence shell, 8 electrons, doesn't need any more, doesn't want to give up any, it's satisfied just the way that it is. All of these other elements are going to bond in a way to achieve this full valence shell, and we'll talk more about that in the next unit. So there's your concept, Lewis dot structures. You've got your practice problems. Go ahead and knock some of those out before class next time.